While physical testing is essential, numerical modeling allows us to efficiently prove a component's safety at a lower cost. Aerospace structures, like jet engine components, operate under extreme thermal conditions, ranging from 600 to 1500 degrees Celsius. My name is Guilherme Caldeira, and my project's goal is to build a robust simulation environment to test and optimize a jet engine nozzle. To start, a literature-based model was recreated in ANSYS using a two-step approach. Firstly, the nozzle wall temperatures were calculated using ANSYS Fluent, a computational fluid dynamics software. Secondly, the structural stresses and displacements were obtained within ANSYS Mechanical, a finite element-based structural software, by importing the temperature fields mentioned before. The baseline CFD model used simplified boundary conditions, like constant heat transfer coefficients, inlet temperatures, and velocities. The structural FEA followed suit, using material properties, an internal pressure, and a rigid fixed support. By recreating these exact conditions, the project successfully matched the baseline results with less than a 10% margin of error. More importantly, this validation exposed several oversimplifications in the baseline study. Firstly, relying on constant heat transfer coefficients forced the use of a virtual wall, a non-ideal CFD practice. Moreover, applying a simple, rigid fixed support introduced massive non-real parasitic stresses by unnaturally restricting the nozzle's thermal expansion. To fix this, the physics were upgraded. Firstly, a conjugate heat transfer simulation with precise inflation layers to capture the true thermal boundary layer phenomena was implemented. Structurally, the 3-to-1 kinematic constraint was applied. This secured the part, while allowing free thermal expansion, revealing the true, physically accurate stress state. With the artificial stresses removed, we proved that the part suffered mainly from two distinct real thermal loads. First, an axial gradient, caused by the temperature dropping from the hot inlet to the cooler outlet. Second, a radial through-thickness gradient, acting between the scorching interior walls and the cooler exterior exposed to natural convection. With a highly accurate model established, we move to the final phase, a parametric optimization. By varying the nozzle wall thickness, we learn that walls that are too thin lack structural stiffness and suffer under the axial temperature changes. Conversely, walls that are too thick act as a severe thermal insulator, generating massive radial temperature gradients. The results proved that the structural sweet spot was exactly 2 mm. At this thickness, we achieved a 47% mass reduction. Ultimately, the project delivered a lighter, safer, and thoroughly optimized aerospace component. Thank you for your time.